Welcome to the E-Pathshala lecture series in computer architecture. This module we are going to look at some advanced concepts of ILP, namely dynamic scheduling. So the objectives of this module are to discuss about the advanced techniques for ILP, how do you exploit ILP using advanced techniques, and also discuss the Tomasulo's dynamic scheduling algorithm. So just to do a recap of instruction level parallelism that we have discussed so far and how you can exploit it further, we know that all microprocessors since about 1985 have used pipelining to overlap the execution of instructions, and that has really improved performance. So overlap of instructions is called basically instruction level parallelism, since the instructions can be executed in parallel. Now basically there are two different techniques or separate techniques to exploit ILP. You can use the hardware approaches or dynamic approaches which will try to exploit parallelism. So here the hardware becomes more complicated. The other approach is using static approaches, that is the compiler based approaches, which will rely on the software and do instruction level parallelism exploitation. Now if you look at the hardware approach or dynamic approaches which we have already studied, this dominates processors like the Pentium 3, Pentium 4 and all the multi-core architectures that we are looking at today. And we know that if you look at the pipeline CPI, it is the ideal CPI for the pipeline plus all the hazards that might increase the pipeline's CPI. So you have the structural hazards, you have the data hazards, and you have the control hazards that might increase your pipeline CPI. And the ideal pipeline CPI is a measure of the maximum performance that is attainable by the implementation. Now if you are looking at only a set of instructions, a basic block, and you are trying to exploit instruction level parallelism within that, you have a problem. Now what do you mean by a basic block? The basic block is the sequence of instructions without a branch instruction. It is a straight line code sequence of instructions without a branch instruction. So you have only one entry point and one exit point. But with the frequency of branches being very high, it is not possible to have a large basic block without any branches. So we have hardly about 4 to 7 instructions in a basic block. And most of these cases what will happen is these instructions are also dependent on each other. So the basic block does not give you too much of opportunity to exploit instruction level parallelism. So we will have to obviously look at exploiting parallelism beyond these basic blocks or across multiple branches. So multiple basic blocks. So we will have to look at loop level parallelism. So it is not just enough if we look at the basic block, we will have to look at exploiting parallelism at a much higher level by looking at multiple basic blocks. So one easy target is loop level parallelism. So try to look at loops which are independent of each other and try to exploit the loop level parallelism there. Now in order to exploit loop level parallelism, one architecture that is normally used is a vector architecture and vector processors. We will discuss about vector processors in a later module. Now if we are not going to use vector processors, then we will either have to look at dynamic branch prediction or static branch prediction if it is a compiler based approach, and try to unroll the loop based on the prediction that is offered by these predictors. So if it is a dynamic branch predictor that we are looking at, we are going to do a dynamic unrolling of the loop, and if it is a static branch prediction that we are looking at, we are going to statically unroll the loop. So we will have to look at these techniques now and see how the unrolling of the loop happens and how we are going to handle the loop level parallelism. And if you look at the hardware and software, they should always work together and preserve the program order. That is, the order in which instructions would execute, if executed sequentially, will always have to be maintained. Just because you are doing a parallel execution, the program order cannot be changed. And you will also have to make sure that all the dependencies have been taken care of, and these dependencies do not lead to any hazards in your pipeline. So if you have name dependencies, you know a name dependence does not have a true data flowing between two instructions. It is only the name that is common between instructions. So, if at all you have a name dependence, if the name is changed, this dependence can be handled. So, register renaming is a common process for handling name dependencies, and register renaming again can be handled either by the compiler or by the hardware. So, we are just looking at different techniques which will help solve our problem, help exploit instruction level parallelism, and we know that the hardware also can offer the solution as well as the software can handle this, offer this solution. And we will also have to worry about the exception behavior. Just in the previous module, we looked at what are exceptions and how exceptions can complicate pipelines. Now, preserving exception behavior is again vital to the implementation of the pipeline. Because you've reordered the instructions or dynamically executed the instructions out of order, you should not raise unwanted exceptions. No unnecessary additional exceptions should be raised in your program just because the order of execution was altered. And we will also have to worry about the data flow. You will have to make sure that the actual flow of data among instructions that produce results and those that consume them will have to be maintained. And this data flow will obviously be modified by your branches. Branches make the flow dynamic, and that will determine which instruction is a supplier of data. So, while handling control dependencies, you will have to make sure that both data flow and the exception behavior are maintained. While handling name dependencies, we will have to make sure that name dependencies are handled, and register renaming is a common process for handling name dependencies. So, we know that basic block is not enough to exploit parallelism. So, we will have to look at loops. Loops become easy targets for exploiting parallelism. While exploiting the parallelism available in loops, we may have to do an unrolling process. So, the unrolling can be done dynamically by the hardware or it can be done by the software. While unrolling, you may have to take care of all the hazards that might occur. So, name dependencies will have to be resolved. You will have to make sure that there are no exceptions occur. So far we have assumed only static scheduling with in-order execution, and we have looked at how hazards can be handled in a statically scheduled pipeline. Now, we will introduce the concept of dynamic scheduling. So, static scheduling is the compiler has optimized the code, it has given you a schedule and the hardware just executes it in that sequence. It does not look at reordering the instructions. Now, many a times you will find that that is not going to lead to too much of improvement in performance, and the hardware will have to try to execute the instructions out of order. So, if some instructions are already ready for execution, you do not have to delay those instructions. Those instructions can be dynamically scheduled and they can be executed. So, we will have to look at the concept of dynamic scheduling. So, dynamic scheduling is a technique in which the hardware rearranges the instruction execution to reduce the stalls while maintaining data flow and exception behavior. And unlike static scheduling, it is not possible for the hardware to look at the entire code sequence and do a scheduling process. So, we normally look at a set of instructions, an instruction window, and within those instructions we can see how these instructions can be reordered and rescheduled for execution. Now, the advantages of dynamic scheduling are the fact that dynamic scheduling can handle cases when dependencies are unknown at compile time. For example, when you have a memory reference involved, the compiler may not be able to identify whether two memory locations will cause a problem. For example, if you have an address as 20R2 and 45R3, there is the compiler has no way of determining whether these two addresses will refer to the same memory location. That can be done only when the effective address is calculated. So, such dependencies cannot be resolved at compile time. So, when you cannot handle these dependencies at compile time, the compiler will not be able to reschedule the code. So, all those cases will be handled at runtime. So, that is a major advantage of dynamic scheduling. It obviously simplifies the compiler. The hardware becomes more complicated, but it definitely simplifies the compiler. And it allows code compiled for one pipeline to run efficiently on a different pipeline, because the pipeline hardware automatically takes care of the optimizations. And it is also possible to introduce advanced concepts like hardware speculation, which is a technique with significant performance advantages. This technique can be added to dynamic scheduling. It can be built on dynamic scheduling. So, dynamic scheduling is a hardware approach, and in a dynamically scheduled pipeline, all instructions pass through the issue stage in order, but from the issue stage they get out of order. So, they bypass each other depending upon the availability of operands. So, execution happens out of order, and obviously completion also happens out of order. So, the issue is in order. After the issue stage, they go out of order depending upon the availability of operands. So, even if a later instruction has operands ready for execution, it can enter execution even though the earlier instruction has not executed. So, it enters execution out of order and obviously finishes execution also out of order, not because of the fact that it entered execution out of order, but because of the fact that it also has varying latencies. We already have looked at a floating point pipeline which has variable latencies. So, even because of the variable latencies, instructions will finish out of order. And scoreboarding was the foremost technique that was used for dynamic scheduling, but scoreboarding has some disadvantages. It was later refined and the Tomasulo's algorithm was introduced. So, Tomasulo's algorithm is the most popular dynamic scheduling technique which handles all hazards appropriately. So, we look at the Tomasulo's dynamic scheduling algorithm. So, the key idea behind dynamic scheduling and the Tomasulo's approach is allow instructions, even instructions behind a stall to proceed if they have the operands available, and instructions that can execute in parallel, you allow them to execute in parallel because you have multiple execution units. So, you will have to really make use of these execution units. So, the hardware is never a problem. So, you have enough hardware to execute these instructions. So, allow these instructions to execute in parallel. Now, look at a typical example here. So, you have a divide instruction which divides two data and writes into some register F0, a floating point register. Following that, you have an add instruction which is dependent on the divide. Add uses F0 as one of its source operands. So, there is a true data dependency between these two instructions, and it will give rise to a raw hazard. But if you look at the third instruction does not use F0. So, you have its operands already available and there is no problem in executing the sub instruction. But if we do an in order execution, what will happen is sub D is unnecessarily getting delayed because of add D being delayed. Add D, you do not have a question of executing it because there is a true data dependency. Now, what do you do with that? If you want to allow sub to execute, then we go in for out of order execution. So, even though add has not executed, we want the subsequent instructions to execute just because its operands are available. If the operands are not available, it will anyway stop. That is a different issue. But here the operands are available, so I'll allow them to execute because the operands are available. So, we would want to have an in order issue, but we want to go in out of order execution and it will also finish out of order. So, even though add stalls, the sub instruction has no reason to stall, it has no dependencies. So, we would want the sub to execute. If we have to do this, we will have to bring a slight change in the way we looked at the issue stage. If you recall what happens during the issue stage, you know that the fetch happens first, and during the issue stage, two different things happen. One is the decoding of the instruction itself to find out what the instruction does and checking for structural hazards. And also we go ahead and read the operands, read the register file, get the operands from the register file, do a sign extension of the immediate operand and all that, so that you have all the operands ready before you enter the execution stage. Now, what we do is, if we are maintaining the issue stage as such and we want an issue stage to do both the issue operation as well as the read operands operation, if in the earlier example, if the add instruction has not decoded, because add cannot read its operands now, it has a data dependency with the earlier instruction, add cannot read its operands. So if add does not read its operands, then sub also cannot read its operands. Sub does not read its operands, it cannot execute. So this option of having a decode operation as well as read operands in your issue stage is not going to help us do dynamic scheduling. So we slightly alter our the way we look at the issue here. So we want to have an in order issue, but out of order execution and out of order completion. So what we do is we split the issue stage into two stages. We look at the issue as consisting of only decoding the instruction and checking for structural hazards. Read operands will automatically happen when operands get available and become available, and once operands become available, the instruction will automatically enter the execution stage. So thus that is the major change that is brought in. So during the issue stage, we only look at decoding the instruction and checking for structural hazards. Once your add instruction gets issued, you know that the sub instruction can issue. It's still an in order issue. Add will be delayed at the issue stage, it will not enter the execution stage because it does not have operands to execute, but sub has been issued subsequently. Sub can enter execution because its operands are available. So you have a lot of advantages for dynamic scheduling. Of course, you also have some disadvantages here. There is a substantial increase in the hardware complexity because the hardware has to keep track of what happens in the pipeline when an instruction finishes one stage of operation and enters the other stage. Where will it write into, all that information will have to be maintained by the hardware. So that bookkeeping will have to be done by the hardware. So there is a substantial increase in hardware complexity. It also complicates exception handling because all these instructions are executing out of order and all that. So your out of order execution will also give rise to out of order completion. So it also creates the possibility of war hazards. War hazards, earlier itself we had war hazards in a floating point pipeline, but we did not have war hazards earlier. Now reading instruction operands out of order will also lead to war hazards. So all these will have to be handled. So the idea of dynamic scheduling is when with all this changes that are brought in, we should still be able to execute the instruction without giving rise to hazards. You cannot have any of these hazards happening in the pipeline. So if you look at these instructions, what the Tomasulo does is it tracks and finds out when operands are available, and it uses, in order to do resolve name dependencies, it uses the concept of register renaming. So all the concepts that we discussed earlier, so it will do a dynamic unrolling of the loop based on the branch prediction. It will do register renaming in hardware in order to avoid your war and war hazards. All these concepts are brought in your Tomasulo's approach. And the register renaming basically eliminates the war and war hazards. Now, how is register renaming done? This just gives you an example of the register renaming process. So here you find that there is a dependency with the name dependency with the F6 register because it's the same register that is being used. There are of course data dependencies also, but the name dependence is only with respect to the F6 register. So how do you handle this name dependence? So if you just use a different register, you see that the name dependence has been resolved. So if you use a different register called S and T here, the name dependencies have been resolved. So the program now just has a true data dependencies, which will definitely have to be handled. So by just using the renaming process, register renaming process, we've dealt with data dependencies, and true dependencies alone will have to be handled. So how does the Tomasulo's approach do a register renaming process? Now what we are trying to do here is, associated with every functional unit, you have what are called reservation stations. So if you have a floating point adder unit, you have a few reservation stations associated with the floating point adder unit. If you have a floating point multiplier unit, you have a few reservation stations associated with the floating point multiplier unit. Now these reservation stations help in doing the renaming process. So when an instruction is being issued, during the issue stage of the instruction, you decode the instruction and check for structural hazards. And the main structural hazard that is checked for here is checking for the availability of a reservation station. So, if there is no reservation station available, it becomes a structural hazard. And if there is a structural hazard in a particular instruction, that instruction cannot be issued, and because it is an in-order issue, you cannot issue subsequent instructions. So, if there is a reservation station available, then this instruction can be issued. Now, what the reservation station does is, the reservation station has a data structure in such a way that it can buffer all the operands for that instruction. So, if you look at what the reservation station contains, it contains the information about the instruction, it buffers all the operand values when it is available. So, when you are issuing an instruction, if that instruction already has the operand available, you just read it from the register file and store it in the reservation station. If you do not have the operand available, then you say that some other instruction has to produce the result for you. So, that is what is contained in your reservation station. We will anyway look at the complete data structure as we proceed. Now, the reservation station basically fetches and buffers an operand as soon as it becomes available, and once operands become available, it automatically enters the execution stage. So, while execution, you do not have to read from the register file, operands have already been read from the register file and they have been buffered into the reservation station. So, the reservation stations are the ones that help you do the renaming process. Now, suppose if you have issued an instruction to a reservation station and that has a true data dependency with another instruction, so you will have to wait for that instruction to finish. Then what you do is you designate the reservation station which is going to produce the result for you. Say for example, we looked at a divide instruction earlier. So, divide would have been given a reservation station entry. So, when add is issued, add does not have both its operands available. One of its operands is read from the register file and stored in the reservation station. The second place, you just say that the divide instruction, when it finishes, it has to produce the result for the add instruction. And you designate an instruction, once an instruction is issued, you designate an instruction by the or identify an instruction by the reservation station tag that is allocated to the instruction. So, you always identify, it is a unique identification, you identify an instruction by the tag of the reservation station to which it has been allocated. And once the instruction has both its operands available in the reservation station, it automatically enters execution when the functional unit becomes available. So, once the result is ready, the number of clock cycles in which this instruction remains in the functional unit will depend upon the latency of the instruction. So, once the instruction is completed, all the results of each and every functional unit is broadcast on what is called a common data bus. So, all the functional units are connected together by means of the common data bus. This common data bus updates the register file. It also updates all the reservation stations. So, any reservation station waiting for this data that arrives on the CDB will grab in that data. So, the CDB transmits the data in a form as it gives the reservation station tag and it also gives the data. So, the register file which is waiting for that reservation station data will take in the data. The reservation stations which are waiting for the data will also grab in this data. And basically this is the renaming process that happens, and the renaming process takes care of your name dependencies, and it also handles your war and war hazards. We will look at an example as we proceed. And just like you have reservation stations for the functional units, you also have reservation stations for your load and store instructions. So, they are basically called load and store buffers. So, the load store buffers will basically buffer the address, the effective address, and if it is a store buffer, it will also buffer the operand. So, a store buffer will have an address component and a data component, whereas a load buffer will only have the address component. These act like reservation stations for your load store units. So, we basically have only 3 stages in a Tomasulo's algorithm apart from the fetch stage. Fetch is the usual stage, so we are not elaborating on the fetch stage, no change happens there. Apart from the fetch, you have 3 stages. The first stage is your issue stage. Issue stage is when you get the next instruction from the FIFO queue, from the fetched queue, and check for structural hazards. The checking for structural hazards is basically checking for the availability of a reservation station. So, if there is a reservation station available, issue the instruction to the reservation station, and also get the operands if they are already available. So, for example, if it's a divide instruction, because once you've decoded the instruction, you know what instruction it is. For example, if it's a floating point divide instruction, I am going to allocate this floating point divide instruction to the reservation station allotted to your floating point divider unit. So, allocate this instruction to a floating point reservation unit. So, this instruction from now on is going to be identified by that reservation station tag, and if the operands, if the operands are already available from the register file, just read them from the register file and store them in the reservation station. If the operand values are not available, this instruction cannot proceed to the next step. It will wait in the issue stage itself, and it will keep checking the CDB, waiting for the operands to become available. So, the next step is the execution stage. An instruction moves from the issue stage to the execution stage when operands become available for the instruction. So, that depends on the data dependency. So, when an earlier instruction which has to produce data for this finishes, the operands are broadcast on the CDB, and when operands become available, these instructions obviously enter the execution stage, and these instructions are going to remain in execution depending upon the latency of the instruction. The next stage is, once an instruction finishes completion, the results are transmitted on the common data bus, and that is what is called the write back stage or the write result stage. So, the results are written onto the CDB, and whatever is written onto the CDB goes into all the reservation stations. It also goes into the register file. So, any register file waiting for this data will take in the data coming in on the CDB. Any reservation station waiting for this data and the store buffer, which is also a reservation station, will grab in this data that comes in this CDB. And one thing that you will have to remember is, if it's a store instruction, a store can execute only after the operand becomes available. So, if you have already calculated the address, just have the effective address, and stores must wait until the address and the data value are received. Now, so having looked at the basics of a Tomasulo's algorithm, we look at the reservation station components here. So, the Tomasulo's approach basically looks at maintaining 3 different data structures, at least 2 different data structures in hardware. The third one is only for understanding purposes. So, the most important data structure is the reservation station. So, the reservation station components, you have a tag on the name to identify the reservation station uniquely. You have an operation field which tells you what type of operation is going on in that reservation station. A VJ, VK fields, which are the value fields. So, if the value of the data is already available, you just store them in the VJ, VK fields. If the values are not available, then the QJ, QK fields will tell you which reservation stations are going to produce the operands for you. So, it is either the VJ, VK fields that get filled up or QJ, QK fields that get filled up, but an instruction goes into execution only when the VJ, VK fields get filled up. And also busy status indicating whether the reservation station is busy or not. The second data structure that is maintained in a Tomasulo's approach is the register result data structure, which tells you which reservation station's data is going to write each one of the registers. So, for all the registers, we will indicate which functional unit is going to write into each of these registers. If there is no pending instruction to write to these registers, there will not, it will just remain blank, you do not have to indicate anything. The third data structure that is used is, of course, an instruction status, which is more for understanding purposes. So, all the 3 data structures have been shown here. So, you have an instruction status which tells you what is the status of the instructions for each of the instructions in the instruction window, whether it is in the issue stage or execution has been completed or it has reached the write result stage, what is happening. Then you have the reservation station which buffers all the operands and details about the instruction. The third data structure is your result register data structure, which tells you which reservation station entry is to write into each of these registers. So, the Tomasulo's algorithm, this is the functional block diagram of the Tomasulo's dynamic scheduler. So, as you can see, instructions are fetched from the instruction queue, they are decoded. depending on what instruction it is. When you issue the instruction, once you decode the instruction, you know what instruction it is. So, it is either given allocated a reservation station entry associated with the appropriate functional unit, or it is given to a load store buffer, load or a store buffer. Okay. And as soon as the instruction is fed there, you also have the operands being read from the register file if they are available and buffered there. So, this is, and all the functional units are connected by means of the common data bus. So, the common data bus will broadcast the data, and any reservation station or the register file which is waiting for this data will grab this data. So, before we get into the summary, I would like to emphasize on how it handles war and war hazards. Now, war, the reservation station does the renaming process, and that is how your war or war hazards get handled. Now, if you look at a war hazard is basically because of output dependencies, two instructions writing into the same register file. So, when the first instruction is issued, say for example, if both of them are writing into register F6, then when the first instruction is issued, the register result status will say that that instruction has to write into F6. When a subsequent instruction is issued and that is also going to write into F6, then that entry will be modified in your register result status, and it will say that this instruction, which is a later instruction, will have to write into F6. So, that is how war hazards are handled. As far as war hazards are concerned, you know it is again caused by name dependency, anti-dependency, but as soon as an instruction is issued itself, you know that if operands are already available in the register file, you go and fetch them from the register file and buffer them in the reservation stations. So, even if a subsequent instruction finishes execution and goes and modifies the register file, you do not have a problem, because the unmodified value, original value has already been read from the register file and it has been stored into your reservation stations. So, that is how a war hazard or war hazard is handled by register renaming process. So, to summarize, we have seen that ILP can be exploited both by the hardware as well as by the compiler, and it is not possible to just look at exploiting ILP within a basic block. So, we will have to basically look at exploiting at the loop level. So, if you are looking at exploiting at the loop level, you know that we will have to do dynamic unrolling of the loop using dynamic prediction, or static unrolling of the loop using static prediction. Similarly, we will have to do a register renaming process to handle all the name dependencies that will have to arise. So, dynamic scheduling is one technique where we try to execute the instructions out of order as soon as the operands become available. Out of order execution will also give rise to out of order completion. So, we look at an in order issue, we look at an out of order execution and out of order completion. So, dynamic scheduling basically does dynamic reorganization of code at runtime and make sure that no hazard happens. So, it handles all types of hazards, and in order to handle this hazard, it has to do a bookkeeping process, and it maintains 3 different data structures in hardware, and it has 3 stages of execution: the issue stage, the execution stage, and the write result stage for the instructions, and handles all the dependencies and the possible hazards appropriately. Thank you.